Welcome to the fascinating world of remote sensing. In this video, we'll embark on a journey to understand how scientists gather information about the Earth's surface without ever touching it. Remote sensing is a powerful blend of science and technology, allowing us to observe, analyze, and interpret our planet from afar. Whether it's monitoring forests, tracking weather, or mapping oceans, remote sensing plays a crucial role in our daily lives. Over the next several scenes, we'll break down the fundamentals, explore the technology, and see real-world applications. Let's get started and discover how we can see the unseen. So what exactly is remote sensing? At its core, remote sensing is the science, and sometimes the art, of acquiring information about the Earth's surface without making direct contact. This is achieved by detecting and recording energy that is either reflected or emitted from objects, then processing and analyzing that data. Imagine being able to study a mountain, a forest, or even an entire city from miles above, all without setting foot there. Remote sensing makes this possible, and it's used in everything from environmental monitoring to urban planning. Let's break down the process step by step. Remote sensing process involves 7 key elements. First, there's an energy source like the sun, which provides the electromagnetic energy needed to illuminate the target. Next, this energy travels through the atmosphere where it may interact with particles and gases. Once it reaches the target, the energy interacts with it depending on the properties of both the target and the radiation. After that, a sensor records the energy, which is then transmitted to a processing station. The data is processed into images, interpreted, and finally applied to solve real-world problems. Each step is vital for turning raw energy into meaningful information. The heart of remote sensing is electromagnetic radiation. This energy travels in waves, consisting of both electric and magnetic fields that move at the speed of light. Two important characteristics define these waves: wavelength and frequency. Wavelength is the distance between two wave crests, while frequency is how many waves pass a point each second. These two are inversely related. The shorter the wavelength, the higher the frequency. Understanding these properties is essential, as they determine how energy interacts with different materials and how we can use that information in remote sensing. Let's dive deeper into wavelength and frequency. Wavelength is measured in meters, nanometers, or micrometers and represents the length of one complete wave cycle. Frequency, measured in hertz, tells us how many cycles occur per second. The two are linked by a simple formula. As one increases, the other decreases. This relationship is crucial in remote sensing because different wavelengths interact with materials in unique ways. For example, visible light has much shorter wavelengths than microwaves, and each reveals different information about the Earth's surface. Electromagnetic spectrum is a range of all possible wavelengths of electromagnetic radiation, from the shortest gamma rays to the longest radio waves. For remote sensing, we focus on specific regions: ultraviolet, visible, infrared, and microwave. Each region offers unique insights. For instance, ultraviolet can make certain minerals fluoresce, while visible light is what our eyes detect. Infrared reveals heat, and microwaves can penetrate clouds and even some surfaces. Understanding the spectrum helps us choose the right tools for the job. Visible spectrum is a tiny slice of the electromagnetic spectrum, ranging from about 0.4 to 0.7 micrometers. This is the only part our eyes can see, and it's where we perceive color. Violet has the shortest wavelength, while red has the longest. By combining blue, green, and red, the primary colors, we can create all other colors. Sunlight, though it appears white, is actually a mix of many wavelengths. When passed through a prism, sunlight splits into its component colors, revealing the beautiful spectrum we see in rainbows. Beyond visible light lies the infrared region, spanning from about 0.7 to 100 micrometers. Infrared is divided into reflected and thermal regions. Reflected infrared behaves much like visible light, while thermal infrared is emitted as heat from the Earth's surface. Even further along the spectrum are microwaves, with wavelengths from 1 millimeter to 1 meter. Microwaves are especially useful in remote sensing because they can penetrate clouds and are less affected by weather, making them ideal for all-weather observation. Before electromagnetic radiation reaches the Earth's surface, it must pass through the atmosphere. Along the way, particles and gases can scatter or absorb the energy. Scattering redirects the energy, while absorption removes energy at specific wavelengths. These interactions can affect the quality and type of data we collect. Understanding how the atmosphere influences radiation is essential for interpreting remote sensing images accurately. There are 3 main types of scattering in the atmosphere: Rayleigh, and non-selective. Rayleigh scattering occurs with very small particles and affects shorter wavelengths, making the sky appear blue. Mie scattering happens with particles similar in size to the wavelength, like dust or smoke, and affects longer wavelengths. Non-selective scattering involves much larger particles, such as water droplets, and scatters all wavelengths equally, making clouds appear white. Each type of scattering influences how much energy reaches the Earth's surface and how we perceive colors. Absorption is another key process as radiation passes through the atmosphere. Molecules like ozone, carbon dioxide, and water vapor absorb energy at specific wavelengths. Ozone protects us by absorbing harmful ultraviolet rays, while carbon dioxide and water vapor absorb infrared and microwave radiation. These absorption patterns create atmospheric windows, regions where radiation can pass through more easily. Remote sensing instruments are often designed to take advantage of these windows for clearer observations. When radiation finally reaches the Earth's surface, it interacts with various materials in 3 main ways: absorption, transmission, and reflection. Absorption means the energy is taken in by the material. Transmission occurs when energy passes through the material. Reflection is when energy bounces off the surface. In remote sensing, we're most interested in reflected energy, as it carries information about the surface's properties. The proportions of each interaction depend on the wavelength and the material's characteristics. Reflection can be specular or diffuse. Specular reflection occurs on smooth surfaces where energy is reflected in a single direction like a mirror. Diffuse reflection happens on rough surfaces, scattering energy in many directions. Most natural surfaces fall somewhere between these extremes. The type of reflection depends on the surface roughness compared to the wavelength of the incoming radiation. This distinction is important for interpreting remote sensing images as it affects how features appear. Let's look at two examples: leaves and water. Leaves contain chlorophyll, which absorbs red and blue wavelengths but reflects green, making them appear green to us. In the near-infrared, healthy leaves are strong reflectors, which is why scientists use this region to assess vegetation health. Water, on the other hand, absorbs longer wavelengths and reflects shorter ones, making it look blue or blue-green. Suspended sediments or algae can change the color and brightness of water, affecting how it appears in remote sensing images. By measuring how different materials reflect or emit energy across various wavelengths, we can build a spectral response for each object. These patterns help us distinguish between features that might look similar in visible light but are very different in other parts of the spectrum. For example, water and vegetation may appear alike in visible wavelengths but are easily separated in the infrared. Spectral response can also change with time and location, so knowing where and when to look is key for accurate interpretation. Remote sensing systems can be passive or active. Passive sensors rely on naturally available energy, usually from the sun, and can only operate when that energy is present, like during the day for visible light. Active sensors, however, generate their own energy, such as radar or lasers, and can collect data anytime, regardless of sunlight or weather. Each type has its advantages and is chosen based on the specific needs of the observation. Remote sensing: it's important to distinguish between images and photographs. An image is any pictorial representation, regardless of how it's captured. A photograph specifically refers to images recorded on photographic film, usually in the visible or reflected infrared range. Today, most remote sensing data is digital, with images made up of pixels, tiny squares, each with a brightness value. This digital format allows for easy processing, analysis, and sharing, making it the standard in modern remote sensing. Digital images are made up of pixels, each representing a small area of the scene. Sensors record energy in different wavelength ranges called channels or bands. By combining data from multiple channels, we can create color images or highlight specific features. For example, using 3 channels, blue, green, and red, we can display a true color image. If we use infrared instead of one visible channel, we can reveal details invisible to the naked eye. This flexibility makes digital remote sensing incredibly powerful. We've just completed the fundamentals of remote sensing. We've covered the basics of electromagnetic radiation, how it interacts with the atmosphere and the Earth's surface, and how sensors capture and process this information. Understanding these principles is the foundation for exploring more advanced topics, such as different types of sensors, image analysis, and real-world applications. Whether you're interested in environmental science, geography, or technology, remote sensing offers a window into our world like never before. Do you know that 3 of our 5 senses, sight, hearing, and smell, are actually forms of remote sensing? They allow us to gather information from a distance. The other 2 senses, taste and touch, require direct contact. This simple fact highlights how remote sensing is a natural part of how we experience the world, not just a technological marvel. Remote sensing isn't just for satellites and scientists. It's part of our daily lives. Ultrasounds, weather maps, speed radar, and even graduation photos are all examples. Hospitals use CAT scans and MRI to see inside our bodies without surgery. Even bats use sonar to navigate in the dark. These are all forms of non-intrusive remote sensing, showing just how versatile and widespread this technology is. Concepts of wavelength and frequency are not just important for remote sensing, they're also behind the Doppler shift. This phenomenon explains why the sound of a passing train changes pitch as it moves toward and then away from us. The same principle applies to light, helping astronomers measure how fast stars are moving. It's a great example of how fundamental physics connects to both everyday experiences and advanced science. Color is more than just what we see. Hue refers to the specific wavelength, what we call color, while saturation describes how pure that color is. For example, pink is a less saturated version of red. Understanding these properties helps in interpreting remote sensing images, where subtle differences in hue and saturation can reveal important information about the Earth's surface. Rainbows are a beautiful demonstration of scattering and refraction. Water droplets act as tiny prisms, bending sunlight and separating it into its component colors. Shorter wavelengths like violet and blue appear on the inner arc, while longer wavelengths like red and orange are on the outer arc. If there were no scattering in the atmosphere, shadows would be pitch black, but thanks to scattered light, they appear in varying shades. Colors we see are a result of how objects interact with light. If an object reflects all visible wavelengths, it appears white. If it absorbs all visible wavelengths, it looks black. Most objects reflect and absorb different wavelengths to varying degrees, creating the rich palette of colors we see in nature. This principle is fundamental in remote sensing, as it helps us interpret what different colors in an image mean about the surface being observed. Cameras are a great example of both passive and active sensors. On a sunny day, a camera simply records the sunlight reflected from objects. This is passive sensing. Indoors or on a cloudy day, the camera's flash provides its own light, making it an active sensor. Similarly, police radar guns use active sensing by emitting pulses and measuring their reflection to determine a vehicle's speed. These everyday examples show how remote sensing principles are all around us. Photographic film excels at capturing fine spatial detail, thanks to the sensitivity of individual molecules. However, digital sensors outperform film in spectral and radiometric qualities. Digital sensors can record extremely fine spectral bands, allowing for detailed analysis and fingerprinting of targets. They can also capture thousands of brightness levels, making them ideal for scientific and practical applications in remote sensing. Can remote sensing use anything other than electromagnetic radiation? Absolutely. While most remote sensing relies on electromagnetic energy, other forms like sound are also used. For example, sonar uses sound waves to map the ocean floor, and even a telephone conversation is technically remote sensing, gathering information at a distance. This broadens the scope of what remote sensing can achieve. The sun is the most obvious source of electromagnetic energy for remote sensing. Our eyes are natural remote sensors, detecting visible light from the sun and allowing us to see. This simple fact connects human perception with advanced technology, showing that remote sensing is both a natural and engineered process. Can we take photographs in the infrared range? Yes and no. There are special films for the reflective part of the infrared spectrum used in both science and art. However, there are no films for directly capturing thermal infrared heat, as this would require keeping the film extremely cold. Instead, electronic sensors are used to detect and record thermal infrared images, expanding our ability to see heat. Most remote sensing systems avoid ultraviolet and blue wavelengths because they are easily scattered and absorbed by the atmosphere. Ozone absorbs most ultraviolet radiation, protecting us from harm. Rayleigh scattering affects blue light more than red, making blue light less likely to reach the Earth's surface. That's why remote sensing often focuses on longer wavelengths for clearer, more reliable data. Best atmospheric conditions for remote sensing in the visible spectrum are clear, sunny, and dry days with minimal pollution. At noon, when the sun is directly overhead, the path through the atmosphere is shortest, reducing scattering and absorption. These conditions ensure the most accurate and detailed remote sensing data. Ever wondered why you can see the dark side of the moon during a crescent phase? The light comes from the sun, reflects off the Earth, then bounces to the moon and back to your eyes. This long journey of light is a great example of how reflection works in remote sensing, revealing details that aren't directly illuminated. To deepen your understanding, explore a remote sensing glossary. It's filled with definitions and explanations of key terms from spectral response to atmospheric window. Whether you're a beginner or an expert, having a solid grasp of the vocabulary will help you navigate the field with confidence. Scientists use their knowledge of radiation and atmospheric interactions to develop radiation products, specialized data sets for environmental monitoring. These products help track everything from land cover changes to pollution and climate trends. By understanding how radiation behaves, we can create tools that support decision-making and protect our environment. Microwave remote sensing is especially important in Canada and other regions with frequent cloud cover. Microwaves can penetrate clouds, rain, and even some vegetation, making them ideal for all-weather observation. This technology is used in applications like soil moisture measurement, sea ice monitoring, and disaster response. Spectral fingerprinting uses the unique spectral response patterns of different materials to identify them. By analyzing how objects reflect or emit energy across various wavelengths, scientists can distinguish between soil types, vegetation, water bodies, and even man-made structures. This technique is fundamental in environmental studies and resource management. Remote sensing is a cornerstone of environmental monitoring. It allows us to track changes in forests, monitor crop health, observe urban expansion, and detect natural disasters. By providing timely, accurate, and large-scale data, remote sensing supports sustainable management of natural resources and helps us respond to environmental challenges. In agriculture, remote sensing is used for crop type mapping, monitoring plant health, and managing irrigation. By analyzing spectral data, farmers can detect stress in crops early, optimize fertilizer use, and increase yields. This technology is transforming modern farming, making it more efficient and sustainable. Foresters use remote sensing to map clear cuts, identify tree species, and monitor forest health. By tracking changes over time, they can assess the impact of logging, disease, and fire. This information is vital for sustainable forest management and conservation efforts. Remote sensing helps hydrologists monitor floods, measure soil moisture, and track water quality. By observing large areas quickly, scientists can respond to natural disasters, manage water resources, and protect communities from flooding and drought. In polar regions, remote sensing is essential for monitoring sea ice type, concentration, and movement. It also helps detect oil spills, track ocean color, and study coastal features. These observations are crucial for navigation, climate research, and environmental protection. Remote sensing is a powerful tool for mapping land cover and tracking urban expansion. By analyzing changes in vegetation, built-up areas, and biomass, scientists and planners can manage growth, protect habitats, and plan for sustainable development. Remote sensing provides detailed maps of the Earth's surface, including planimetry, digital elevation models (DEMS), and topographic maps. These products are used in navigation, engineering, and environmental management, offering precise information for a wide range of applications. As technology advances, remote sensing continues to evolve. New sensors, improved data processing, and expanded applications are opening up exciting possibilities. From monitoring climate change to supporting smart cities, remote sensing will play an even greater role in understanding and managing our world. Stay curious and keep exploring, there's always more to see from a distance.